cracking. So that means we will completed all syllabus for the chapter 4. All right. So before this, you've already learned on how to design the main reinforcements, right? Okay, so now we proceed the design for shear reinforcements, or also we call it as the links. Okay, if you look at here, we have two patterns of cracking. So the at the middle one is normally will occur the vertical crack. Okay, call it as a vertical crack because the cracks directions almost in 90 degrees. Okay. So normally the directions of the crack almost 90 degrees. So that is vertical cracks that is caused by a bending stress here. Okay, then another one we have a diagonal cracks that have a slope here. Okay, so these ones call it as a shear cracks. Okay, which the cracks, the cracks that we will resist by the shear reinforcements. Okay, so the angles of these diagonal cracks in between 22 degrees up to 45 degrees. So kalau you nampak cracks within this slope, within these angles, so you can consider that one as a shear cracks. If more than it, it becomes a vertical crack here. So because of these vertical cracks, that's why you provide the main bar. Okay, according to the bending stress, which is according to the bending moment maximums. For shear reinforcement here, okay, it because of diagonal tension, which is it from this shear stress here because of this shear force. That's why we provide the vertical links. Okay, especially at the shear regions. Okay, this is the shear region from point load to the supports. Okay, let's say have a 2-point load here. This is the shear region. Okay, whereas the positions of the vertical link. While the middle one here, the middle span is the bending or flexure region. Okay, so that's why vertical links will be provided especially at the shear region because this is where the shear diagonal cracks will occur. Okay, so this shear, okay, it based on the shear force, okay, that you get from the shear force. Again, what's the maximum of V max here will be as a reference. How many reinforcement of shear reinforcement will be provided according to the V max. All right, so I hope you understand. Okay, why we provide the main bar, why we provide the shear, how we provide the main bar is according to the bendings, maximums, moments, and how we provide the shear reinforcement based on the shear forces. Okay, so this is more on theoretical. I make it simple. Okay, for concrete itself, okay, for shear reinforcement, if you look at here, this is a example of the length, which is half of it, a part of it is in the compressions area and another is in the tensions area. So actually the shear here is resisted by the concrete and also resisted by the shear reinforcements. Okay, so there's a contribution from the concrete resist the shear and also a part of shear reinforcement that will resist the shear. So that's why we call it as a strut inclinations method, which is it's like a commitment from the concrete, from the compressions, and also from the shear reinforcement itself. Okay, so before this, okay, before previously actually, let's say this is the main bar that it provide at the tensions reinforcement, while this is the top reinforcement, okay, or the compression reinforcement. Previously, we arranged the shear reinforcement in inclined position. That means in these directions. Okay, kita susun dia sengit-sengit macam ni sebenarnya dulu. Okay, and then there will be a cracks, right? In diagonal directions. So let's say this is the cracks that will occur. Okay. So the angles of the crack will between about 22 to 45 degree, which is 45 degrees angle. This is the maximum, the critical one of the cracks here. Okay, so it's like we resist the cracks by crossing the cracks there. Okay, dia macam kita crossing tu kita halang balik, kita resist balik all the stress there. So that's why previously actually we arranged the shear reinforcement in these directions, but once we want to apply at site, actually it's quite complicated, it's quite difficult because we have to arrange in diagonal positions. Okay, so easy to also make a simplification, which is currently, okay, commonly we just arrange the vertical links in the links in the vertical direction, but the crack still can be resisted by this shear reinforcement, although it arranged in a vertical directions. Okay, so that is why if you look at the theoretical here, which is the D1 here is a line for shear reinforcements. Okay, which is it's like we crossing the verticals, we crossing the cracks, the diagonal cracks. Okay, with the opposite directions of the shear reinforcement. Okay, so this will be the common arrangement for the shear reinforcement here. So if you look at here, this is what it called as the inclination strut method. Okay, so which is this is all the cracks here. Okay, so this is all the cracks. Start loading. Okay, this is all the cracks line here. Okay, and then there will be a concrete crushings at the compression zone, and then this is the vertical link that we provide to resist all the shear cracks here. There will be a resisted by the VC, which is the shear for the concretes, and then also resisted by the VS, which is VS is from the links. Okay, so all these VS will resist the shear stresses. Okay, and also for the shear of the concretes. All right, so for design for shear, okay, there will be a few of equations that you need to be used. Okay, I will not go into details, but this is the final equations, okay, of the VRD max. Okay, 0.36 FCK. FCK is a grid of concrete. B is the width of the beam. D is the depth of the beam. Okay, so which is it included here angles. Okay, theta, cot theta, and tangent theta. Again, because of shear have angles. Shear crack is a diagonals position directions. So the angles is will be between 22 to 45 degree here. So that means you need to know that angle, is it in 22 or in 45, but it should be within between this 22 up to 45 here. All right, so then from the links that we provide, we can calculate its shear resistance. Okay, so just includes all the information of FYK, what's the yield strength of the reinforcement that we provide. Okay, and then ASW, which is the area of the link. So this is the links that you provide. You need to know what is the area according to the diameter of the link. So let's say you provide a H10. So from H10, you need to refer to the tables in order to determine what's the ASW for this link here. Okay, in order to know the shear resistance of the links that you provide. Okay, so other equation here, if based on the distance, if you already know the distance, so then you can use of this equation. If not, you that means you just determine the size of the bar, so that means you have to use of these equations. Okay, then another formula that you have to use is this formula. Okay, once you already know the it's ASW and also of VED. VED is come from the shear force. Okay, from the Vmax actually, from the Vmax of the beam that will carry the shear load here. Okay, so this is VED, and then ASW is come from area of the links that you provide. Okay, from here you will know what the spacings also for the links. Is it H10 sufficient to be 200 or 150, depends. Okay, the load and also the diameter, the area of the links that you provide. Okay, and then next will be a minimum. Okay, there will be a minimum value. Remember for this beam here, we have a so if I draw according to the shear diagrams, so daripada beam ni katakanlah dia punya shear diagrams ini okay, so this is the locations the value of the Vmax, right? So from the Vmax, you will provide the reinforcements. Okay, you will provide the reinforcement, but there will be a V minimums here. Okay, that what it's mean by minimum or AS divided by S here. There will be a V minimum here. This is where's the location of the links according to the Vmax. Okay, which is up to certain length here. There will be another value which is V minimum. So this is example. This is where the V minimum. From this V minimum, there will be a ASW minimum according to this V minimum. So this is how the formula that you will get the spacing, another spacing for another shear links, okay, according to the V minimum. So that means there will be another arrangement, okay, for V minimum, okay, according to the V minimum. This is arrangements according to the V max. Let's say from the V max is a H10 for 200. So that means you have to arrange these links with the spacings of 200. Okay, and then up to the certain length here, you have to refer for the V minimums in order to provide the other arrangements. Okay, let's say according to the V minimum is H10 might be up to 300 mm. So there will be another arrangement, okay, of shear reinforcement according to the V minimum. So that is what it means. Okay, and then um, then we have another one here, okay, the maximum spacing of vertical links. Because of we have a minimum, there will be other limitation for the maximum spacing, which is you just need to check, okay, which is the maximums of vertical link should not exceed 0.75 D, which is as the spacing is S max here. Okay, S max here is about 0.75 D. Okay, so this is all the design procedures. Just follow the step, but at the same time, you need to understand why we provide the links according to the Vmax, why we provide the links according to the V minimums here. But some other case, we don't have to provide the V minimum. Okay, and sometimes bila you buat project, ada group yang dah tunjuk kat saya, dia punya V minimum which is higher compared to the VRD. Okay, so in that case, just use the VRD. Okay, so just ignore about the V minimums. Okay. So first you need to determine shear force VED, which is this VED is come from the shear force diagram. VED is a V max that you get from the shear force diagram. That's it. Okay, then you have to calculate for a VRD max. Okay, why? You need to compare with the V max. This is the required. Okay, this is from the design based on the sections that you provide, based on the concretes that you provide. Okay, if you look at here, the parameter here is based on the B, D, and the grade of the concretes that you provide, which is what the capacity of the shear force that provide by the beam sections. Okay, and then this is according to the real load that applied on the beam. So that's why you need to make the comparison. Is it more than Vmax or less than Vmax? Okay, according to these angles here. If you look at in this formula, there's angles here. So that means you need to calculate what's the VRD max according to 22 degrees, what the VRD max according to the 45 degree. You need to calculate this according to these two angles. Okay, just inserts in these equations here, but remember it's already give answers here, which is actually you can calculate this one, right? So kalau masukkan code 22 degrees, you'll get 2.5 here, which is cot theta here is equal to 1 over tangent, let's say 22 degrees. So you will get 2.5. Okay, same goes for the cot 45, which is 1 divided by tangent 45, you'll get 1. Okay, so just 1 plus what is tangent for the 45 here. So if your VED, which is this is a VED, let's say hundreds, kilonewton, it should be in kilonewton because of the shear force. Okay, if more than VRD max, okay, so you have to redesign the sections. Bila redesign the section, that means you have to change the size. Might be make it bigger, the B, make it bigger, the depth of the beams. Okay, so that's when you have to start again back to the beginning. So that is apa, the things that you have to do if you calculate by manual. Kalau software, klik je lah kan, tukar je section dan sebagainya. Kalau manual, you kena patah balik, return back from the beginning about the sections of the beams. Okay. Okay, then if VED less than VRD max, so that means you have to use this code 2.5 for the 22 degrees here and calculate the, you can proceed by calculate the shear reinforcements that need to provide for the beams. Okay, so then another case once it between it, okay, which is you need to use for this code theta of 1.0, and then theta here is for the checking what's the real angles for the cracks. It should be within 22 to 45, right? But it just need to know what's the angles actually for that cracks. Okay, for that shear. All right, so then you can calculate the shear links there, and then this is equation for the minimum slings, and then this is another thing. It's about how to calculate the additional longitudinal tensile force caused by the shear. Okay, so if you look at the beam here at shear regions, okay, especially at the shear regions, there will be a main bar. Jangan internet saya trouble sudahlah hujan kan kat sini, buruk. So at the shear region, it consists of a main bar, of a longitudinal tensions bar, and also vertical sling, and also the shear reinforcement. That means there will be a shear force also will be distributed to the longitudinal bar. So that's why this is just need to check either this reinforcement bar at the shear region is enough or not in order to resist the shear forces. So just calculate use of all of this equation. You already know what's the VED, what the Vmax, and then what's the angles. Okay, is it 22 or 45 there? And then compare with the moment. Okay, this is moment from the moment max divided by the sex here. Okay, so it should be more than this FTD here. Okay, so then you need to determine additional tension reinforcement. What's the AS? It should be within this shear region. Okay, if let's say you dapat AS ni is about 2H16. Okay, so look at check the reinforcements that you provide. Let's say from the beginning, AS that you provide is about 4H16. Okay, but once you do the calculation for the additional tension reinforcement, it gives answers about 2H16. So that means 2H16 is already provided by 4H16. So that means at least 2H16 of longitudinal bar must be provided within this shear region. Okay, so that is what is meant by additional longitudinal tensile tensions reinforcement. All right, so this is how to calculate ASW. Remember, because of the links have two legs, right? So you have to multiply the area. kalau dalam chart the area, okay, in this chart, this is according to the one leg, according to the one bar of reinforcement. Because of this sure reinforcement, we bend, make it as a one loop, right? That's why we have a one bar and also another one bar. That means there will be a two diameter here, two area here. So that's why you have to multiply the area by 2. Okay, so that's mean the ASW for this size 8, okay, area dia adalah 101. Okay, by multiply the 50.3 by 2 legs here. All right. So if you look at here, this is table 2, which you can refer about how to select spacings of the bar. So normally this is the common spacings that we provide. 50 or 75, 100, which is a quite simple numbers of spacing. Janganlah you provide 60 mm. It should be about 50 by 50. Okay. Ataupun 75, which is jangan 53, 105, jangan buat macam itulah, jangan complicated sangatlah. Make it simple, okay, make it easy, especially that thing will be applied at site. Okay, so from the calculations, if you get if you use H ataupun R8 here, okay, so you dapat ASW, let's say 251, so that's mean you have to use of this R8 200s or R8 250. If you look at here, once you make the spacings more closer, kalau 50, that's mean in 1 meter, okay, this is per meter, this is for every 1 meter. So 50, that means every 50 mm there will be a link, every 50 mm there will be a link. That means this is the closest spacing that you can provide. So then let's say for this 300, so there will be a longer spacings, right? Every 300 baru ada satu link, every 300 baru ada satu link. So that's mean once you decrease the spacing, actually you increase the area of reinforcement that you provide, because more closely spacing will provide high numbers of reinforcement compared to this 300 spacing, which just, let's say, provide about 300 at the same 1 meter of the beams. Okay. So that's it. So let's go. Let's see. We go for example. I also believe some of you in the project you already calculate for this year. So mungkin you lebih faham kan once I explain about the shear. Alright, so if you look at this example for simply supported, so you nampak kat sini, it give a shear force here. Okay, so dari bending, you dah settle dah in provide the longitudinal reinforcement bar according to the moment maximums. Okay, so kalau simply supported lah, kalau continuous banyak more than one spacings, right? Let's see, one or more than one spacing, which is there will be a several moments that you can refer. Okay, either you can provide the reinforcement moment by moments ataupun just according to the moment maximum. Which one the maximum, there will be the reinforcement that will provide for the whole of the beams here. Okay, kalau simply supported, just one span is according to the one single maximum moment. Macam ni lah. Okay, sama juga dengan shear. So, which is, this is the maximum shear, which is 168, which is, this is VED, okay, for this span. So, VED is 168. So, you need to compare with VRD max. Okay, compare with VRD max here. So just use of this equation, find out what's the VRD max. If use theta 22 degrees, find out what's the value for VRD max if theta is equal to 45 degrees here. So there are two VRD here, compare with the 168, compare with the VED. So from here, it shows that VED less than VRD max, okay, and then also VED less than VRD max of 45 degrees. So that means you can use of angles of 22 degrees. So this one pass, you can proceed. Don't have to return back, redesign the sections and so on. Okay. So by using angles of 22 degrees here, so you can do the checkings, okay, of a theta. So this is a 10 degrees here, which is the actuals of the cracks of that beam. So you can proceed by calculate the ASW here, okay, divided by S for the shear length that you need to provide according to the VED, according to the VED here. So just replace of VED and then it's FYK, dia punya depth, okay, and then what's the cot theta? It's a 2.5, right? Okay, or this theta. Okay, 2.5. So includes in the equations. So dapat nilai ASW, which is ASW, oh yeah, ASW divided by S is equal to 0.297, atau make it simple as a 0.3. So from this ASW divided by S equal to 0.3, try what's the diameter of links that you want to provide. From, let's say you want to use size diameter 8 mm here. So 8 mm. So what's the ASW? Refer in the tables. Okay. Kalau pergi balik dalam table tadi, H8. So ni H8. Remember, it should be account for the two legs, two area, right? So it's about, for this link, this is the ASW. For the links, okay, because we consider about the two bar or two legs of the shear reinforcement. So H8, the ASW is 101. So pergi balik. So that's why ASW for the H8 is 101. So masukkan balik dalam equation ni, you will get the spacings. Okay, you will get the spacing. So spacing is 101 ASW divided by a ratio that is 0.3. So the spacing is a 339. Okay, then you have to check the maximum spacing as max, which is, it should be 0.75D. This is the maximum spacing. So that means the spacing that you provide should not more than the S max. So dapat tadi 339, okay lah, you can provide H8 Remember, this is 339, but if you provide more closely than 339, that means you provide high area of the reinforcement, right? High numbers of reinforcement. Makin rapat, makin kuat, makin rapat, makin banyak reinforcement yang you provide. So that means 339 mm takkanlah nak provide 339 mm kan, dia kena marah dengan Pak Indon kan. So make it simple. Let's say you want to provide 300. Boleh je. In this example, it provide 3 to 5. You not provide 300. Or might be you want to provide about 275. It's okay. Okay, it's also correct. But again, it's about the cost. Once you make the reinforcement more closely, lagi rapat, lagi banyak reinforcement. So that's the things also that you need to consider in terms of the safety and also the cost of the projects. Okay, so once 339, if you provide about 3 to 5 or 300, that one just nice. Okay, according to the spacing required for that beams. Okay, then we have another one for minimum links. So remember, we have another one which is this is according to the V minimums. Okay, yang dapat tadi VED. Okay, from VED you will arrange the reinforcements here for HA 2 to 5. Okay, then stop at the certain lengths, and we'll continue with the continue with the shear reinforcement according to the V minimums. Okay, because this area it becomes to be the flexure zone. That means you don't have to provide high numbers of reinforcements according to the V max, because it becomes to be in the flexure zone. So just provide the V minimum, just provide the links according to the V minimums. Okay, so same, you have to use of these equations, get a ratio of ASW divided by S, which is, this is ASW divided by S, which is 0.179. From this, you have to select, you have to determine what's the size diameter of the links. Let's say same H8. Normally kalau links we provide diameter 6 or diameter 8, which is the smaller ones. Okay, so let's say H8. What's the ASW for the H8? Inserts in this equation, replace it, you will get the S here. You will get the spacings. Okay, but look at of this spacing is the 562, which is more than the S max here. So that's why you have to use the S max. Okay, nampak lebih besar kan? But this is the limitations of the spacings. Okay, so you need to use for the S max. Okay, so that means you have to use H8 4 to 5 or 400, depends. Okay, and then from this H845 that you obtain, you can calculate what the shear resistance of minimum link according to H845 here. Okay, because ASW is based on 101, and then S is a spacing which is 45. Replace in the equation, you will get V min is 134 here. So this is how we do the arrangement. This is according to the V max or VED, and then this is according to the S minimum. Okay, 134. So just make a ratio between it. So you will get what's the length, what's the length should be provided for H8 to to 5, 3 to 5, and then you have to stop and then do the next arrangement according to the V min. Okay, if you look at here, this is where the regions that the beams more into flexure zones. Okay, then this is more into the shear zone here. So that's why you will provide this reinforcement, this shear reinforcement more closely compared to the reinforcement according to the V min. Okay, ni dah makin jarak. So that's milling zone makin kurang. Okay, so this is that is how to provide to arrange the reinforcement, shear reinforcements. And then this is it's actually for the checking. Is it the main reinforcement that you provide? Is it enough or not to resist as a part resistance for the shear? Okay, calculates the additional tension force according to these equations here. Just consider about its VED. Okay, and then this is cot theta. Ni it's a 2.5 because some of the example they use Excel, so dia ada titik perpuluhan kan, so this is tadi kita lihat example they use about 2.5, right? Okay, so here dia punya force of tensions here is a 208. Okay, then make a comparison with the moment here, which is the moment is more than FGD. So you can calculate what the additional area for the tension reinforcement. From here, need to use 2H20, but previously it provide about CH20. So that means this is quite enough, sufficient enough, because for shear region, it only need to have 2H20. Okay, so that means there will be a detailing. Okay, detailing. Contoh, let's say this is the beam. If you look at from the top view, tengok dari atas. Okay, so ada 3 bar. Nampak dari atas 3 bar. Kalau nampak daripada cross section, actually ada 2 layer kan, ada 2 layer. Nampak dari atas from the top view, you just look at about this 3 bar. Actually is a 6 bar. Okay, so again we have a shear region, we have a flexure region. This main bar is from the bending moment. Okay, it for flexure or for bending reinforcements. So that's mean within pergi pula pada side pergi pula pada side view. Okay, this is the main bar that you provide, which is 6H20. Okay, actually this 6H20 tak perlu tak perlu provide. It not necessary actually to provide for the whole length of the beam, because this 6H20 it's very important, very special for the flexure zone. For the flexure zone, because of this is where's the maximums, right? Which is this is area that should have 6H20, but once it up to flexure zone, once it up to shear area, shear zone, you can reduce the numbers of this reinforcement because it becomes the shear area which just resisted by the shear reinforcement by the links here. So that's why if you calculate this additional, that means at least it should have 2H20 here. This part also, both sides 2H20, because this 2H20 combined with vertical links here, it good enough, is strong enough to resist the shear, which is VED tadi 168. So that's why in detailing there will be a cutting. Dia kadang-kadang dia susun, dia akan ada bila sampai sini ni ada 6H. Bila dekat shear ni mungkin dia hanya panjangkan bar 2H20 saja. Dekat area sini ada 6 bar. Dekat area sini ada 6 bar. It's a bit crowded. Okay, this is for flexure. Once it becomes shear, because of shear is just enough for 2H20 plus with the vertical link. So just panjangkan, tak payah buat cutting lah. Tapi sampai sini mungkin ada buat cutting untuk reinforcement yang tak diperlukan. If you want to do the cuttings reinforcement, if you want to cut the reinforcement because of the cost kan, nak jimat for the economic reason and so on, ataupun just guna 6H20 for the whole length pun boleh, but it backs about the cost. Alright, so that's it for the shear. Any questions? Any questions before I proceed with the deflections? Maybe you can relate with your projects. Siapa yang dah buat mungkin dah jumpa isu-isu yang you not really understand. Any questions?
Doktor, kalau continuous base pun buat macam ni ke? Kalau continuous?
Continuous, sama. It should also provide the links. You can also refer the example of continuous, right? There are notes for the continuous here. Okay, but this one is kalau lihat contoh ni, ataupun you can see the examples in UTM here. Okay, so see the examples, another notes, right, from the UTMs. Okay, the same things. Every reinforcement should provide with the reinforcements. Okay, which is you have to find out what is the VED, is a V max, right? Okay, and then you have to compare with the VRD, and then what's the data that should be used. Okay, what's the reinforcements. Okay, what's the minimum.
Kenapa VD bukan terus ambil shear dapat? Kenapa kena kira lagi?
What VED?
Tengah sini VD.
This one.
Atas sini. Tengah sini. Yang terbawah. Tadi dia ada kira dekat yang itu example continuous bin. Yang slide lagi satu. Yang slide.
Sekejap. Saya nak tengok dia punya apa ni? Beginning notes je. Alright, so this one is VED 138, right? So they use the VED 138. Okay, from it you will get the VED and also Vmin. Okay, and then the transverse still in the flange. So this is a concrete strut in the flange. So this one.
Yeah.
Look at all this continuous one. Kalau VED, this one is from the load analysis, right?
Ya.
Ah, mana tadi? Oh, this one, right? Why it's used in the flange here? This is a VRD max, right? Which one? Ni salah ni VRD ni.
Oh, dia tulis salah.
Ni salah ni VRD sebab nampak ni dia salah type ni.
Yang lagi example, yang slide lagi satu, yang example continuous bin.
Continuous.
Yang slide, yang tadi
This
tukar
one.
tukar. Tukar.
Hah?
Yang slide lagi satu.
Lagi satu.
Yang tadi total share punya. Example continuous base.
Not this one. Example berapa? 6 point?
Bukan, dia satu slide saja. Yang slide ketiga, slide keempat. Yang total share punya. Kan ada 4.6, 4.7, example split, example continuous, lepas QTM.
Atas lagi ke?
Ke saya share, saya letak dalam group. Total, yang slide ni. Yang tadi, yang saya letak dalam group. Yang example VED dia. Kenapa dia guna formula lain?
Sekejap you letak dalam group. I nak buka I punya Telegram pun slow ni.
Kenapa VED dia guna formula?
Okay. Ni another cases. If it mentions, okay, I buka sini ya. Alright. Okay. So soalan ni. Cuma, okay, one more thing before that. Bila I tengok contoh ni, it just two spans, right? Actually, you couldn't use of this table. It mentioned the number of span is less than 3, but still dia guna tables, right? Something wrong actually with this example. Okay?
Boleh.
Kan? Alright. So ni dia based on the loading. Okay, so for the support B criticals, I'm not sure the details of these examples. Might be kalau lihat kat sini, okay, actually shear at the center support is this one, kan? Dah dapat actually this one shear about 192. Okay, but from the solution it gives here, it's like that they want to know what's the shear at these cracks here. So that's why there will be a D distance here. Faham tak? Just for the normal calculation, we just use of this 192. Might be the details of this question, it asks about what's the shear at this point. So that's why it recalculate back. Actually, this is 192. So that means it becomes at this distance, because of this D distance, it reduce about 1 something like that lah. Tapi you punya calculation just based on this Vmax, okay? Don't
So untuk
confuse.
calculation, untuk projek ke exam kami terus guna VMAX dah
Yeah,
cukup lah.
yeah, yeah. But the exam depends on the questions, right? Depends on the questions. But as long as you understand, kalau just commons, we just use of this Vmax to to determine the links for this beam. Tapi kalau macam ni, might be the question ask about the details at this point or at this point. Dia more critical lah. Okay. But I can say that we will not go for this extent for the question, right? Okay. Any questions
Tak
lagi?
ada.
Yang lain-lain? Alright, so kita pergi kepada checking So alright, for this checking, we do the checking for the cracking. Kita nak lihat is that width is safe or not. Okay, and then deflections also. What's the deflections of the beams according to its spans and beam sections, and then detailing. Actually detailing is not our job. It's not our job. It's for draftmen, kan? Kita ada draftman, kita dah sketch everything as that we want to provide. So then the real situation actually we just pass that designs to the draft persons. Okay, so they will do the detailing. They have a procedure where to cut, how many percents to cut, and so on. But this at least we have to know basics, just a simple detailing. Okay. Okay, so for the cracking, if you look at here, this is all 4 types of cracks that can be found, commonly occurs of the beams. Okay, so the first one is a flexure tensile stress. Of course, it's more vertical directions, and then diagonal tension stress is more inclined diagonal that have a slopes. Okay, remember for the shear cracks, it consider once the cracks occur between 22 up to 45 degree. The 45 degree is the critical one. Okay, while this one is a volume change due to shrinkage, thermals, chemical effects, might be quite special case lah. Okay, and then splitting. This one also common. That means there is a crack along the reinforcements that it divide the reinforcement with the concrete cover. That is splitting. It's normally because of the bonding. Okay, there's a bonding between reinforcement and concrete thread. So because of the bonding failure or anchorage failure. Okay, so cracking, we do the limits for the width of the cracking. Sometimes we found the cracking is not so serious kan. Kita tengok, oh kecil je lebar cracks tu, tak bahaya kan. Kalau kita dah tahu what's the limits of the crack. Kalau tak tahu, tengok je cracks, orang dah takut kan. Okay, so not only because of the aesthetic reasons kan, tengok cracks tu macam it's not safe for that building if have many cracks, because that cracks, some of the crack is not because of the structure failure. Okay, it because of the finishes, it because of the workmanship. The plaster tak betul, tak cantik, that's why cracks because of the thermal, temperature, weather dan sebagainya, not because of the structure. So we have to know the differences, what's the cause of that cracks. Not all cracks is dangerous. Okay, So to control the crack, it have two alternatives. There are two methods here which you can refer in EC2 section 7.3, either by control of cracking without direct calculation ataupun calculations of crack widths here. Okay, so this is the limitation of the crack. It can be limit about 0.3 mm for all exposure class, or might be can be extends to 0.4. Okay, either 0.3 or 0.4 is according to the exposure class, but normally we go for 0.3. But uh, just for these two classes, XO and X1 can be up to 0.4. Okay. So you can imagine once we not do the limitation for the cracks, right? So there will be many things can be go inside the cracks. Hujans, chemicals, kan? It can cause the corrosions of the reinforcement and so on. Okay, so that's why we have to do the limitation for the crack, and also for the aesthetic value, for the appearance um, for the structure. Okay, so this is the first method on how to control the crack without direct calculation, which is you can just check the minimum reinforcement area. Okay, what's the minimum reinforcement area, which is AS mean. This is equation for the AS mean. Okay, so that's why once you do the calculation for AS, first you buat calculation for AS required, right? What the required AS that should be provided, and then you propose um, the AS provided. Then at the same time, you have to check with the AS minimum, what the at least minimum size should be provided. Okay, by using of this equation, and at the same time, there will be a S max, the maximum one. Once it have a minimum, there will be a maximum. Okay, so there will be this to checking actually after you do the calculation for AS required and AS provide. Okay, so from the AS provide, let's say you dapat AS provide according to 2H 16. So what's the AS provide according to 2H16? So then you have to compare, check the limitation. Is it between AS minimum and AS maximum? So if within the limit, so that means you can proceed by use of this reinforcement. Okay, so that is how the checking actually to control the cracks. Okay, then maximum spacing of reinforcement according to the table 7.3n, and another one maximum bar size according to table 7.2n. There are two tables, okay, need to be referred here for maximum spacing and maximum bar size. So this is a where's the table? 7.3. Okay, this one dia dah lompat ke sini pula table ni. Okay, so these two table, what is still stress here? This is the still stress. That means you need to calculate what the Fs here. Okay, so katalah this is for bar diameter, this is for bar spacing. Okay, maximum one. Okay, let's say you calculate, you dapat Fs about 240. Okay, so what's the crack width? Let's say the common one is 0.3. So that's mean you punya maximum bar diameter is a 16. Okay, same goes for this bar spacing here, let's say 240, the common crack width is zero 0.3, so that means you put the maximum bar spacing is 200. What it mean by bar spacing is a spacing between the reinforcements. Okay, so the spacing here, the maximum one. So the maximum one. All right. Then if you look back of this equation, it have a FCTM here. This FCTM is from table 3.1. Nampak sini FCTM divided by FYK. Okay, and then B is a width. Okay, is a width. Kalau French, it should the web width. This one is a BT also. This one is a BT also for the rectangles, but not less than 0.0013. Okay, BD. Okay, so this is a table 3.1. You can check in the EC2. There are many value at the first column here. According to the FCK, it's not so clear in my slide. Let's say grade 30. So what the FCTM for grade 30 this is the value for FCTM here. Actually, this is also the strength for the cylinder. Okay, so which is 2.9 here. Okay, this is from the tensile test. Okay, so 2.9 will be used in this equation. 2.9 divided by FYK. So FYK, let's say 500 and so on. Okay, so that is how we do the checking. Okay, from the AS provided, compare with the AS min and AS maximum. And then these two from the table. All right, so we go for a spacings. Okay, we go for a spacings. Why we also need to control the spacings? We have a minimum. We have to check the minimum spacing because it want to permit concrete floors around reinforcement. Okay, so you can imagine once you provide too many numbers of reinforcement, it become crowded in the beam sections. The beam, the width of the beams not so big, right? It's just about 200 or might be 150. So how come you need to ensure that all the concrete mixture or the fresh concrete will be coated all around this congested reinforcement, right? So that's why we need to provide the minimum spacing between the bar. Okay, so there are three comparison here, which is you need to compare these three. Should not the spacing of the bar should not less than the maximum from these three. Okay, let's say the maximum bar size. Just look at in this beam section. Let's say the maximum one is a 20 mm. So this is 20 mm. Ada juga 16 mm. So might be level 1 you provide all 20 mm. The second level here you provide 16 mm. So that means this is the maximum bar size, which is 20 mm. Then the maximum aggregate size. What's the aggregate size that you use for the mixture? Okay, so kalau dekat lab sini selalu kita guna 20 mm. So let's say 20 mm aggregate size plus 5 mm. Okay, so it will be 25 mm. 20 mm is specified in EC2. So that means this is the limitation that is proposed by the EC2. Kan, EC2 pun tahu aggregate selalu guna 20 mm. So that's why might be use at 20 mm here. So 20 mm. So you compare between these three. So this is the maximum one. So the spacing should not be less than 25 mm in order to ensure that all the aggregates or the cements or the mixture can be coated all around the reinforcement because it's about the bonding, kan? Should have a bonding between the concrete and the surface of the reinforcements. So kalau provide tadi clear distance is about 20 mm. When it says about clear distance, it should be between surface of reinforcement to the surface of reinforcement. This is the clear distance, let's say 25 mm. So if you provide sufficient clear distance, so that means any let's say aggregate tadi guna 20 kan, so boleh muat lah, boleh fill in this distance. Alright, then we go for a deflections here. So to control the deflection, it have two alternative methods here. Okay, might be some of you also dah calculate for the all of these checkings, right? Deflections for the projects. Some of the groups really advanced. Ada yang masih confused lagi. Okay, it's about yeah, take times, right, for you to understand. But from the projects, you can understand what's the some of the problems during the creations process. Daripada situ you belajar untuk more understands, right, all the designs process. Okay, for control of deflection, two alternative method here. Okay, is by a limiting span to depth ratio, and then another one just according to the actual deflections. Okay, so for the limits, okay, we have the first one is the limiting. So this is the limitation that should be considered. Okay. Final deflection of beam, slab or cantilever is subjected to quasi-permanent load, which is just a common load, should not exceed span divided by 250, which is L over D. Okay, should not exceed which is L of 250 here. Okay. And then another one, it should not exceed span divided by 500. So this one will take place after the application of finishes or fixings of the partition. This is a other case. Okay, contoh macam dah siap and then dia nak pasang finisher dan sebagainya. This is once during the constructions. Okay. Alright, so so this is the equations. Okay, once the span effective depth ratio, which is L over D. Okay, according to the controlling limits of span divided by 250. Okay, so this is also in EC2. You can find out these equations. Okay, so if span divided by 250, so you need to use of these equations. Okay, you need to use of this equation, but it have a two comparisons here. Okay, which equation you need to check this one first. Okay, rho more than rho O or rho less or equal than the rho O. Okay, so rho here is actually the reinforcement ratio. Okay, it's the reinforcement ratio. This one, rho here, rho is equal to AS divided by BD, if I'm not mistaken lah. It S divided by BD. While rho O is from these equations. So you need to calculate this rho according to the area that you provide divided by BD, the beam sections. We need to know the reinforcement ratio um, uh, according to the beam sections. Okay, so that is what is meant by rho here, tension reinforcement ratio, and then compare with the rho O here. If in this case, though, so that means you have to use of these equations. So in this equation, it just consider about all the rho that you already calculate. So that means you can calculate this one first, then you need to choose which equations that is related to. Okay, in this equation have also a k value, which is you can use of these equations, these tables. What's the value for the k? Depends, right? Kalau simply supported, k 1.0. Kalau continuous for the end span, 1.3. For interior spans, 1.5. Okay, kalau slab, so tak pergi pada slab lah. Kalau cantilever, about 0.4. Just refers of this table for the key value. So after calculates the L over D, so you dah calculate tadi kan, L over D, either this equation or this equation depends on the rho and rho O here. This L over D need to make some modifications. So ada lagi dia punya additionals or modifications need to check according to the situations of that beam, which is L over D. You have to multiply either by this situation or this situation or this situation. So multiply by 1, multiply by 2, multiply by 3. Okay, if required. Okay, depends the condition of the beams. Okay, let's say for flange sections, okay, just modification for flange sections. Kalau L over D for rectangles tak ada, so tak adalah darab dengan these modifications, which is you have to multiply by 0.8. If the ratio of the flange width, this is flange width, to the web width exceeds 3. So you need to check which is B flange divide by B webs, okay, exceeds 3. If more than 3, you have to multiply L over D with 0.8. If not, tak payah consider. Kalau relate with this situation, you have to consider of this modification. You have to multiply with 0.8. Same goes for the second case. For beam and slabs, okay, other than flat slab, which spans exceed 7 meter. Kalau span tu about 8 meter, so you have to consider this second modification, which is the value should be multiplied by 7 divided by span, which is multiplied by 7 divided by, let's say 8 meter, divided by 8 meter. Okay, the third modifications, where more tension reinforcement is provided, then is provided, then that required AS required. Okay, that means if AS that you provide more than AS required, but should not greater than 1.5. Kalau AS that you provide more than AS required, but should not greater than 1.5. That means less than 1.5. You have to multiply this value, okay, which is A as provided divided by A as required. If more than 1.5, you can just ignore of this modification, these third modifications. Okay, so that is how we do the deflections control. So look at of this example. Okay, so it already provide all the reinforcement here, 2H16, 4H20 for the main bar. Okay, so check the deflections of the beam. So that means for the deflections of the beam, it according to the numbers of bar, according to the beam sections for the beam size, and also the lengths of the beams. It not related to the shear force, shear reinforcement, and so on. It's according to the longitudinal bar, according to the this tensions per beam section and also length. Okay, one it gives all of these data. All right, so this is the equations, right, that you need to use. But which equation? We have the two equations, right? Is it rho more than rho O, ataupun another one equation rho less than rho O? So you need to check what's the rho here, which is AS required divided by BD, and then what's the rho O here. Okay, this is the equation for the rho O. So 0.009 is more than rho O. So that means you have to use these equations, okay, um, um, to calculate of ratio of L divided by D. Okay, the span divided by effective depth ratio. So why we calculate rho prime here? Because of if provide the reinforcements. Okay, if provide the reinforcement. Kalau tak provide compression reinforcement, so you just ignore of this this equation. So zero lah. Okay. What else? Okay, so just insert all the value of rho O, rho and rho prime here. So dapat 17.08. So 17.08, you have to multiply with all three modifications, right? So you need to check, is it that modification relate or not with the situation of that beam. So the first one, modification factor for span greater than 7 meter. So span dia 8 meter. So look at backs here. Okay. This one, right? The second modification, spans exceed 7 meters. So you have to multiply 7 divided by span. So that's why in this L over D, so you have to calculate 7 divided by span, which is L over D, which is 17.08. You have to multiply by 0.88 here, modification for span greater than 7 meter. Okay, then second one, modification factor for steel area, which is AS provides divide by AS required. It should be less than 1.5 here. Okay, so this one is less than 1.5, so you have to consider this modification, which is 1.03. So because of this is not flange, you look at back, this is for flange modifications. Sebab contoh ni adalah rectangle, so that's why just ignore the flange modifications. It's not related to this beam. So that's why L over D darab dengan modification for span greater than 7 meter and also multiply with the modification factor for steel reinforcements here. So L over D allowable. This one actually is a L over D allowable. Okay, which is 15.48. You have to compare with L over the actual. The actual one, the actual length, which is 8,000 divided by 650. And the punya ratio for the actual one, which is 12.23, which less than the allowable one. So that's it. That means you pass the calculation for the diffraction. That means you can proceed to use all the things that you provide in the beams. Okay, so that's it. for the deflection, and then this is for the detailing, how you do the arrangements, how you do the cuttings for the beams and so on. Okay, so once you provide, you have to give detailing for whole of the beams, right? What's the arrangement for the links, and then do the cut sections, how it looks like once you cut the sections. Okay, kadang dia ada tunjuk sini kan. So this is the cut sections of AA, right? There will be a sections A, A. But if you do the cut section at here, there will be a difference because there's a reductions of reinforcement here because of the detailing. Kan tadi I mentioned about the shear reinforcement. Not all of reinforcement is necessary to be proceeds along the end of the beam. Some of it can be reduced, okay, because of this shear region. What's the required actually reinforcement should be provided in this area. Okay, so but some of the designer might be they just use the whole reinforcement up to the end of the beam. It's subjective. It depends on the designer. Okay, but mostly they will do a detailing. Okay, you can imagine this part also, the end of the beam also, there will be positions of the columns. The reinforcement of the beams will be combined with the reinforcement for the columns. So if we not do this cuttings reinforcement, there will be too many reinforcements, okay, in this part. So that's it's ni baru part of the beam. There will be another apa ni uh, another sections of the beam, right, at these first columns. Okay, so there will be a lot of reinforcement at this part here, so that's why we do the detailings. um, if you look at here, this is how the simple detailing, which is at the end there will be just a 50% of reinforcement will be provided at this length here. Okay, let's say for this length of 0.08 L here will be provided about just 50%, but 100%, let's say this one about 6H20 should be provided within this area 100%. Tapi bila nak sampai hujung, kita boleh kurangkan reinforcement. Tak semua kita akan proceed to the end of the beam. About, let's say at this part, about 3H20. We do the reductions, numbers of reinforcement. Okay, this is simple detailing, and this is more details kalau continuous beam, because it consider the main reinforcement at the midspan and also the reinforcement at the supports and so on. Okay, that's it for checkings. You also can refer in the example the same things, okay, which you can refer this example also in the UTM examples kan. So which is you need to determine all the row here and then which row that you need to use, because it have two equations, and then do the modification if it related. Kalau tak, you just ignore. It's like that's apa ni? You give some discounts for L over D. First one is a 14.4. Okay, look at here, L over D is a 14.4. Once you do the reductions, so it becomes 14.2 here. Okay, so then you have to compare with the L over the actuals and so on. All right. Any questions? This will be the end of the design after you provide all the reinforcement and then the links. Then you can start for the checking for cracking, checking for deflection. That's it. There are two checking for cracking and deflection. That one is a serviceability checkings. Okay. Um, uh, According to the load, according to the beam sections, and then the last one should be come out with the detailing. Okay, some of you also asked me about the summarize, right? Summarize in the project. So which I can suggest, which is you can do the summarize in the tables. Okay, some of the students do it in the table. I think that one more um, easy. Okay, once you do the summarize in the table, because for the drawing, for the actual drawing, at the end you have to summarize all the beams. Okay, at side we just look at all the summarized beams for each of the grid line beams. Kan, kita tak tengok pun calculation, kita just refer all the beams. So that is purpose in the project. You have to come out with the summarize of the beam. Okay, let's say this is the ground beams. Okay, you can give a apa ni, the beams grid line here, beam apa, beam A, grid line 1 2 3. So you can draw the detailings and then also the sections of the beam. Okay, so then next beam A 1 2 or 4 and so on. So just summarize in the table. I think it's quite good, okay, for me to check in. All right. So, any question? That means I've already complete for this chapter 4. By next week, we will go for timber designs. Okay. We have another 2 chapter. Next week we go for timber designs. And then the last, not last week's. Just a simple for the pre-stress, just an introduction. It's not apa ni, contributes to any designs and so on. Just a brief about the pre-stress. Alright, so any questions? Ada soalan tak? Nak tanya-tanya projek ke? Yang dah kira? I turn on the attendance in the auto systems. You can submit the attendance. Okay, so semua senyap. So tak ada soalan katnya. Okay, might be later. Okay, once you go through your project, might be there will be a issues on it. Okay, you can come to my office, discuss about your project. At the same time, actually you do the exercise to prepare for your exams. That's the thing, that the same things will be apa ni, designs, calculations that you will face during the exams. You have to design the beam, either rectangle beams or flange beam or simply or continuous. That's the things in the exams. Tak ada lain, memang tu je. Alright, so if you don't have any questions, so I stop the class. Please submit the attendance in order.